Okay, so my talk is going to be divided into 4 questions. I'm going to answer the first 3, which is why we need thread annotations, what the annotations are and what they do, and also how thread annotations are implemented in Clang. The fourth question is, and that is stuff that I am confused about that I hope to receive some feedback from other Clang developers on. So why we need thread safety annotations. Most of you know at least some of this. Everybody wants to write multi-threaded code, lots of reasons. Multi-threaded code have race conditions that are very insidious errors. They're hard to see in the source code. They don't show up in code review. They're hard to see because the actual bug is caused by an interaction with another thread that is not locally visible when you look at the code. So this is how they get into the code, and once they're in the code, they're hard to find and eliminate because they generate intermittent bugs that you can't reproduce in the debugger, and that you typically don't find during unit tests. So this is a serious problem. So here's a real-world example. This is a bug that appeared in the Google code base, and several man-weeks were spent tracking down this bug. So this is going to be multiple slides. So the first bit is we implement a cache. And this cache allows you to look up a value. And once you've looked up the value, that value is pinned within the cache. So it's going to keep that in the cache until you release the value. And then we defined a global cache, which is protected by mutex. Secondly, we write a helper class to handle the pinning and unpinning for us so that it pins it in the constructor and releases it in the destructor. So far, so good. And here's the bug. Now, show of hands here, how many people look at this code and immediately see the bug? 1, 2, 3. Okay, so this is good. This was not immediately visible to code review because it follows the standard threading pattern. We lock it at the beginning, we do some stuff, we unlock it at the end, fine, right? Well, no. Of course, what happens is that the destructor for lookup value releases the value from the cache after you have unlocked the mutex because it's run at the end of the function. It's already been stomped on by another thread, thus causing the race condition. And so the fix also looks strange when you look at the change list. Someone randomly introduced a pair of curly braces, which you would ordinarily think would be a no-op. But in this case, this is the fix. No new lines of, well, you have lines of code, but no new operations actually added. Okay, so how do we find these kinds of things automatically with thread annotations? So we add some annotations. We say that we've got this cache mutex and a global cache, and these are actually related. So we add an annotation that says the cache is guarded by the mutex using this guarded by keyword up here. And secondly, things which modify that cache now have to be annotated by stating that you have to hold the mutex before you can modify the cache. So in this case, the constructor and the destructor have this additional annotation. And now when you check this function, it will discover that you're calling the destructor at the end of the function after you've unlocked it. And the compiler will actually spit out a warning saying you need to be holding this mutex when the destructor is called. So that's a brief introduction to the annotations. I'm going to go into a little bit more detail about what all they are. So first, some history. As I mentioned, what we're really doing is just like you have types to specify the signature of methods in the interface of methods in the class. These thread annotations sort of specify the locking protocol, the threading interface to a class. They're currently implemented within GCC. The original implementation was done by a Google employee by the name of Lechun. It's checked in upstream. You can look at it in the Annotalysis branch. It's actually used in a number of projects at Google. And the design of it is a little bit of a historical artifact. It replaced some informal coding style guidelines. When we started doing multi-threaded code, the guidelines were, please put these things in comments. You know, if you have stuff protected by mutex, put it in the comment, you know, which mutex protects which thing. And so all we really did is, in the initial GCC version, is formalized these comments and wrote a checker to check them. We are currently porting it from GCC to Clang. The initial port was actually not done by me. It was done by an intern by the name of Caitlin. And it has been handed off to me as the current maintainer. So, as I mentioned, thread safety annotations work a lot like type checking. The basic idea is to establish a locking protocol, associate which mutexes guard which pieces of data. And it, like type checking, it doesn't catch deep errors. It catches the common stupid errors that you make when issuing lots of lock and unlock calls throughout the code. So there's a good reference on the relationship between this and type checking, which is type-based race detection for Java. Very similar system there. Okay, so here are all the annotations that we support, or at least most of them. We have a set of annotations for acquiring and releasing locks, and we have a set of annotations for guarding data and guarding methods, and we have some annotations for deadlocks as well. And we also have a few extra ones that are kind of miscellaneous hacks that I'm not going to cover in this talk. Okay, so this is what the mutex class looks like. This is, first of all, certain classes can be lockable. So you put the lockable attribute on the class. You specify which functions lock the class, which functions unlock the class, and there are several different kinds of locking functions. You can get an exclusive lock, which allows read-write access. You can get a shared lock, which allows read-only access. And you can have that version in try locks, where the return value specifies whether you manage to acquire the lock or not for locking state functions that can fail. You can also do something on classes where the class itself is not lockable, but it is guarded by another mutex somewhere. So here I've put exclusive lock function and unlock function on these two methods, but I specify in the argument to the attribute, I specify the mutex that it's actually locking. And so there's a little bit of naming magic that goes on here. So if we have my object, two objects, obj1 and obj2, if you call obj1.lock, it'll look at this attribute, see that it refers to mu, and then know that it acquires obj1.mu. And so same for obj2. So it can, these things, you're restricted in these arguments to only referring to things within your current lexical scope, but then it'll do some replacements across scopes when it interprets them. Okay, and we've already seen guarded by. That's your basic thing for data members. There's also another one that is pointer guarded by. What that means is it's not the data member itself that's guarded, it's the thing that it points to for pointer types. So in this example, if we modify A without holding the lock, we get a warning. If we modify B, that's fine. We can modify the pointer because there's no guard on it. But if you modify the thing that B points to, then we get the warning. And sadly, we don't recurse. There's no pointer guarded by. So there's some limitations here. You can also guard methods. Instead of using guarded by for methods, we decided to create, for historical reasons, a whole new attribute, which is exclusive locks required. And also, since some mutexes are not reentrant, in order to do deadlock prevention, we have the opposite, which is locks excluded. That means you can't hold the particular mutex. And notice, too, the lexical scoping here. So we have a parameter to this function obj, and we can say exclusive locks required obj.mu. So you can refer to function parameters within the arguments to the attribute. Deadlock detection is fairly simple. The basic thing is if you have multiple mutexes that need to be acquired in a particular order, you can do acquired before and acquired after annotations. And then if you lock them in a different order than required by those annotations, it will give you a warning about that. The tool always generates warnings. At Google, we often compile with warnings or errors, so they become errors in our code base. So that's it for the brief overview of the annotations. I'll describe briefly how they're implemented within Clang. So I'm going to go over the basic algorithm, which is really quite straightforward. This is nothing fancy. And then I'll talk about a few of the implementation subtleties. And I'll talk about some limitations and give you a brief flavor of our experiences working with both Clang and GCC on the implementation. So the basic algorithm is we grab a control flow graph and we traverse the control flow graph, and we always maintain the set of currently held locks. And we're just modifying the set. So if you call a function and the function has a lock attribute, then we add something to the set. If you call an unlock function, we remove it from the set. Whenever you do a load or a store, you check to see whether the appropriate lock is in the set after looking at the attribute. Pretty basic. There's a link to the code if anybody is exceptionally curious. So here's an example. So we've got a bunch of basic blocks in our control flow graph. Every block we have an entry set, which is a set of locks held on entry to the block, and an exit set. And the exit set is then propagated to the successors of that block. Two things that you need to handle are, first of all, join points. The way we handle join points is you take the intersection of the two sets, and anything that's not in the intersection you have to issue a warning on, because we require that you hold the same set of locks going into a join point on both of the branches. Similar requirement on back edges. Is lock sets must match. So, lovely. So here's an example of the kind of warnings you get. So we have an if statement here in which we lock mu2. We only lock it within the if. So as soon as you reach the end of the scope, you're going to get a warning that mu2 is not unlocked at the end of its scope. The while loop is fine, but then we forgot to lock mu1 at the end of the function, so it always generates warnings if you don't match up your locks and unlocks. So if you forget to unlock something, or if you unlock something without acquiring the lock first, it'll generate a warning on that too. All right, some subtleties. So the first big subtlety is in the implementation is parsing, because as you noticed, these annotations actually have full C++ expressions that denote the mutexes. Most annotations that you use, we're using the GCC attributes to do this, but we could also use the C++11 attributes. But most GCC attributes don't have expressions, so there was no support for this. And not only do you have expressions, but you now have to extend the lexical scope properly. So for example, if we have a guarded by this arrow mu, but mu is declared after the original data member, then we need to handle that. And actually, Clang made life really easy there because we have the support for delayed parsing. So I just hooked into that, boom, done. You also have to extend the scope of function parameters to include the attribute of the function. We made a few changes to the parser to handle that. Okay, second subtlety, as I mentioned, we have to do some magic with naming, and that's just a simple substitution of variables for the most part. When you have something in a class that refers to this, then you need to substitute the appropriate object for this. And if you have a formal parameter then you need to substitute the argument of the function call for the formal parameter. So in this case, if we have o1.a, and a is guarded by this to mu, then we substitute the address of o1 for this to get a different expression, and similarly for the function call. Another subtlety is expression equality, because as you notice, especially when you do these substitution, you often get minor variations. So if you take the address of an object and you use the arrow operator, is that the same as just doing a dot off of the object? Similarly, you can have other combinations that simplify it to the same. A tricky bit is if you call a function off an object, are those two expressions equal? Well, in a truly sound analysis, no, they would not be equal. You can't guarantee, unless it's a pure function, that you're going to get the same result every time you call it. But in reality, this arises primarily when people are using smart pointer classes. In that case, if you want to get any reasonable checking, you have to assume that if they used this function to grab hold of a mutex, that's going to return the same mutex every time you call it, because otherwise it doesn't really make much sense. You could try to go further and say, does an array with index I plus 1 equal an array with index 1 plus I? We don't do anything like that. Those are going to be treated as different expressions. You have to draw the line somewhere. A second issue with expression equality, and this is a difference between the GCC and Clang implementations, is right now I'm just looking at variables, but as you might imagine from the name, variables can vary. So if you have in lock and in unlock, but you modified in the middle, the Clang version currently does not detect this. The GCC version does, because the GCC version runs on code after it's been converted to SSA form. So SSA would really make life easier here. So some limitations. I mentioned the thing about join points that prevents things like if threadsafe mu.lock and if threadsafe mu.unlock. Because there's a join point there, it'll give you some warnings that can be irritating at times. Another thing that we have seen in practice is people do something very complicated, like lock and unlock a whole array of stuff. Not much I can do about that. That sort of thing. We do have a way to turn off the warnings. If you have a function of this nature, you can put no thread safety analysis on it, and it will turn off your warnings for you. That's the escape hatch. Another big limitation, this is probably the most serious one, is aliasing. So let's say we want to define a scoped mutex class, one that uses implicit destructors to automatically unlock. You can't do it using the set of annotations I just described, because we do an exclusive lock on im, but then the unlock function is on mu, the data member of the class. These things are set to be equal to each other, but there is no way for the analysis to notice that, so you'll get these two bogus warnings if you attempt to implement this as is. We have a special hack with some additional annotations to deal with particular patterns like this, but it would be nice to have a slightly more sophisticated system that did not require those hacks. Okay. As I mentioned, this is currently implemented in GCC. We're not happy with the GCC implementation for a couple reasons. The first of all is that we had to hack into the GCC parser to handle those scoping issues I mentioned. No one wants to look at the GCC parser. Plus, once we hacked into it, the upstream people decided that they did not want to look at our hacks either. So we can't even check it in upstream. Second problem is that analysis operates on Gimple. The lowering to Gimple introduces a bunch of artifacts and erases some of the C++ semantics. So things that I have run into is type information mysteriously disappears because type checking is supposedly done, but I need those types, thank you very much, don't delete them. Virtual method calls turn into a bunch of pointer arithmetic operations to actually grab the function pointer, so trying to trace back and find your virtual method declaration is a pain. You get control flow graph oddities because the lowering algorithm decides to be overly clever in its attempts to share code. We also get fun optimizations that are declared as local optimizations that are supposed to run after the analysis but have non-local effects on the whole program, thus effectively running before the analysis and confusing things. And the last fun part of working with GCC is the lowering algorithm changes dramatically with every new release. So every time upstream releases a new version, suddenly we get thousands and thousands of false positives in the analysis. So we have good reasons to want to move this to Clang. The good news is Clang has a much better organized code base, much easier to do certain things like altering the parser. Another huge advantage of Clang, you get an accurate representation of the C++ abstract syntax tree. A huge disadvantage of Clang is you get an accurate representation of the C++ abstract syntax tree. C++ is a very complicated language, and the AST is not fun to work with. So whereas in GCC, you'd have just a function call, in Clang, you've got function calls, you've got method calls, you've got constructors, you've got destructors, you've got calls to new, all of which have to be traversed and handled separately. It's very difficult to compare expressions. They haven't gone to the trouble to identify loads and stores directly in the AST, so you have to do it yourself. And as I mentioned, the fact that it's not in single static assignment form makes parts of the analysis unsound. So I'll go over some of those in slightly more detail. But now we're on to, this is places I'd like to go, but where I'm not quite sure how to proceed with the implementation. So we're thinking, haven't decided yet, we're thinking about moving the analysis to the static analyzer. We'd like to move away from using GCC attributes and switch to C++11 attributes. And we'd like to better integrate the thread safety attributes with the type system, which introduces type checking and template problems. These are questions I'd like to think about, so if anybody wants to contact me later or has good advice for me, I would love to hear from you. Please send me an email. Ooh, Nick is pointing at someone who needs to give me advice. Okay. Right. So, as I mentioned, the Clang AST is much harder to analyze than a compiler intermediate language. The LLVM IR would be a lot easier in some respects, except for the fact that we'd then back be in the place that we are with the GCC implementation. I've already talked about the SSA form problem. The loads and stores are another issue. A minor one, really, but irritating, which is that you can't just look at the AST and figure out when a store occurs. You have to always look at everything that surrounds the particular expression that you're seeing. My understanding is the static analyzer provides some of these capabilities and might also solve some of my aliasing and control flow problems, but it's not clear whether that's going to be an appropriate framework to implement this or not. But that's what we're thinking about now, is maybe moving some of this to the static analyzer. Here's the big question, is how to integrate this with the type system. So I mentioned that PT guarded by, we don't have a PT guarded by. GCC attributes can't be attached directly to types very easily. They're only attached to declarations. So that's PT guarded by was a hack. It's very easy to break. Here's an example. We have a pointer, has PT guarded by on it. We assign the pointer to some other pointer, and we set the value of the pointer. Oops, no warning. We just bypassed the analysis. Really, if you're using pointers, it's probably because you're assigning pointers to things. So really, no one uses PT guarded by because its chance of actually catching an error is relatively slim. By the time you write to the pointer, it's been passed to some other routine. What I would like to do is say, this is an int guarded by mu, and then a pointer to that int. So in that case, this would be kind of like the const type qualifier on the type. So if I try to cast from an int guarded by star to an int star, that would be like a const cast. And that should give me some kind of warning because I'm casting from one type to another. I'm casting away the guarded by information. And we'd need to do some additional analysis like that such casts are allowed if you happen to hold the mutex but not allowed otherwise. That would give us much more robust analysis. So the question is, how invasive would this be to the Clang type system? This is not restricted to thread safety analysis because some other people might be wanting to add random attributes to types, and it would be nice to maybe do a uniform modification of the Clang type system that would let you detect when you're casting from a type with one attribute to a type with a different attribute, and then hook into whatever the actual check should be for that. Did we lose? Just a moment. Okay, here's an even bigger problem. And we have somehow, oh well, I'm going to leave that down there. If you have attributes on types, then you can pass those types to templates, and that introduces lots of nastiness with template instantiation. So our rule for thread safety attributes, which I think would probably hold for other type systems, is that they should have the erasure property. That means that if you go through and remove them, then that should not affect the runtime behavior. And if you'll notice, all of my attributes are in all caps. That's because they're actually macros, and the purpose of making them macros is that I can change one header file and boom, erase all of them for things that don't understand the attributes. That's quite important. So if they have the erasure property, that means that if you have two different instantiations of the same template, they should share the same implementation. So if we have a vector of int guarded by mu and a vector of int, we should not get two different instantiations in the runtime code. We should only get one. This happens, the two issues that occur here is that if you have static data members, different instantiations have different members, and the shared instantiation would map to the shared member, and similarly for the pointers to static methods. Those two things make the number of instantiations visible to the runtime code, so we have to control that. However, when you're doing semantic analysis, those attributes still need to carry through. So you have to pretend during semantic analysis that you have two different instantiations. So if we have on the vector the operator brackets, that should have type int guarded by mu in one case and type int in the other case when you're actually doing type checking. So this is going to be a little bit tricky. Once again, this is not unique to thread safety attributes. There might be, if other people are interested in making type qualifiers of various kinds as extensions, we might want to add general purpose support to Clang for dealing with this. Okay, so hopefully I've convinced you that thread safety attributes, maybe solve is too strong a word, but assist in dealing with a real problem. I think there's a lot of work that needs to be done right now. The current implementation is very much pre-alpha, so please don't run out and add these to your million lines of code and then email me tomorrow and say, it doesn't work. I know it doesn't work. I have my own million lines of code that we're going to try to get it working on first, and then I'll tell you guys when it does work. But I would love to hear any suggestions that you email me. Any questions? Yeah.
So maybe you answered that, but if you have a structure which you want to be guarded by a lock and it's passed as a pointer, the object to that, how do you specify the lock to be applied? That's one thing. And the other one is if you have a nest of function calls
Well, this is the advantage of the annotations, is that... Oh, I'm sorry. Yes. So there's a couple different questions. One was if you have a structure that you're wanting to guard with a lock and you're referring to it by a pointer, how do you do it? And the second one is, what if you have a function that calls a function that calls a function, and the lock is acquired in the outermost one? How do the innermost ones know that you've acquired it? So the pointer question is, the answer to that is that's sort of why you would want this to be an attribute on the type rather than an attribute. I mean, you can try to use pt guarded by, but like I said, chances are, as soon as you pass it to something else, you're going to lose the attribute. What most code does that uses the annotations right now is you have an object and the mutex is actually a data member of the object, and that way you can refer to it within the other attributes, and that works. Having one complex structure with a mutex that guards it that's outside the structure right now is not well supported. So in answer to the second question, that's great. Well, we don't need that anymore. The advantage of putting these attributes on function is they become part of the interface to the function. So if you are acquiring a lock in an outermost function and calling several other functions, usually want to assume within the body of those other functions that you hold the lock. Well, that's actually not too hard to accomplish, because you just put an exclusive locks required on the definitions of the functions that you're calling. And so that says, A, you have to hold the lock before entering the function, and it says, B, when I type check the body of that function, I can assume that the lock is held by the caller. So you can easily, it does require that you annotate all of your functions with which locks need to be held. So there is an annotation overhead to this, but the annotation overhead is very similar to the type checking overhead. If you assume that the lock is held within the body, then that needs to be part of the interface to the function. Other questions? Yeah. Lots of warnings. The annotations it's totally static. There's no runtime effect to any of these. It's just a warning pass. But if your annotations are incorrect, then it will warn about them. Just like if your type definitions are incorrect, you'll get lots of type errors when compiling the code. Oh yes, yes. No, it's like a type system, but right now it's not as good as a type system, since a type system provides stronger guarantees than we do. But it's only designed to catch stupid errors. Having a type system does not prevent all typing bugs, especially in C, where you can just cast everything to void star whenever you want to. Similarly with this is supposed to catch the common things, like and it's useful for documentation almost as much as it's useful for catching bugs, in that if you use the annotations, then someone else who goes through and reads your code says, aha, this particular method requires that I hold this lock prior to calling the method. So instead of putting that in the comment like it's normally done, this is now put in, where if he actually does call it without reading the API properly, then it'll generate a warning saying, you shouldn't do that. Yeah.
It seems like adding these annotations might be a large, somewhat daunting task for a code base. I'm wondering if there's some way for a tool to help you out, to tell you essentially.
Yes. So there's several different classes of annotations, and there are inference mechanisms to infer the annotations that are available. So one of our biggest complaints is that there are annotations that are so obvious it just irritates people to have to write them down. Like if I have a method called lock, and it has one line in it in which it locks a mutex, could you not please put the lock function mutex annotation on this method for me? That's a typical complaint. And it's especially, the real problem is when you run into templatized code, where depending on which template instantiation you use, sometimes it requires the annotation, sometimes it doesn't. And it's usually for fairly simple things, like the vector guarded by, for example. But we can't actually do that yet. But there are other, you could do a slightly more complicated one where you instantiate a vector with an ordinary int, there's no guard on it, no annotations are required. You instantiate it with a different thing that has some annotations on its methods, and that may affect operations that the template calls. So it would be nice in those cases to be able to propagate certain things like exclusive locks required up to the top automatically, especially in instantiated code. So yes, that's definitely on our to-do list. It's a common user complaint from this. Other questions? Yeah.
Sun added tool called Lockable to allow you to be observing a function. That you say, if you want to call this function, you must acquire this lockable function.
Mm-hmm.
And then the tool will check the call graph and then
Sounds like a very similar thing. Like I said, this is there have been tools and systems implemented for Java that do much the same thing. The original comments that we based this on, I'm sure, were inspired by other sort of more formal published systems. Other questions? Alrighty then.